Hey guys, in this video I want to show you how to find the x-intercept, also known as the zeros of a polynomial, using the rational zero theorem. Hey guys, and welcome back. Franck here, and if you have not done so already, go ahead and subscribe to the channel. In this particular video, we're going to be focusing on solving for the x-intercept or the zeros of a polynomial. So first thing you should know is that the general form of a polynomial is given like this. It's going to be f of x equals to an x to the power of n plus an minus 1 x to the power of n minus 1 plus dot 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 plus a 2 x to the power of 2 plus a1 x to the power of 1 plus a0 x to the power of 0. Of course, x to the power of 0 is 1, so I just have a0 here as my constant. And as usual, our leading coefficient an should be different than 0. Alright, so you can be given a polynomial in this general form, or you can be given it in a factored form. If you're given it in the factored form, it's very easy to find the zeros because all you have to do is set each of the factors equals to 0 and solve for them individually. But the difficulty comes in when your equation is given in a general form. So for starters, let me give you something that's given to you in factored form. So I'm going to have here f of x equals to x minus 3 in parentheses, then multiplied by 2x plus 5 in parentheses, multiplied by x minus the square root of 2 in parentheses, and then finally multiplied by x squared plus 4. So if I wanted to find the zeros of this polynomial, all I have to do is set each of the factors equal to 0 and solve for them individually. So I'm going to have here x minus 3 equals to 0, which would give me x equals 3. Then I'm going to have 2x plus 5 equals to 0, which should give me x equals to negative 5 divided by 2. Then I can get to x minus the square root of 2 equals to 0. That should give me x equals to the square root of 2. And of course, finally, I can get to x squared plus 4 equals to 0. And if you set the 4 on the other side, you're going to get x squared equals to negative 4. Taking the square root on both sides would give you x equals to plus or minus 2i. I here being the imaginary unit that we covered in our previous lessons. And so when you look at these guys here, the two first zeros are going to be our rational zero because they are numbers that can be written as a fraction of a whole number divided by another whole number, negative or positive. And the next one here is going to be an irrational zero. And finally, our two last ones here, plus or minus 2i, are going to be known as the complex zero. And so the first thing I want to give you that will be useful to you when you're about to find the zeros of a polynomial given in a general form is the rational zero theorem. This theorem says that if a polynomial has integer coefficient and has rational zero written in their reduced form as p over q, then p has to be a factor of the constant term a0 and q has to be a factor of the leading term an. This is very important because it's going to help us guess what particular zeros of polynomials are when you have a degree that's bigger than 2. Because as you know, if a polynomial has a degree 2, then it's a quadratic. And we've already learned how to solve for the zero of a quadratic. And if it's degree 1, then it's just a linear equation, and that's easy to solve too. So our real problem here comes in when the degree of our polynomial is bigger than 2. And so let me give you some examples here so you can see what I'm talking about. So our next example is going to be a polynomial given to you in a general form. It's going to be f of x equals to x cubed plus 2x squared minus 5x minus 6. And so to be able to solve for the zeros of this particular polynomial, since it's not a quadratic or a linear expression, it is not easy for us to just go ahead and factor this thing out because we don't really know any rules for polynomial of degree 3. And so since this polynomial has only integers for coefficient, we can assume that some of these zeros will be irrational. In this case, it will be written as p over q as a reduced fraction. And so we've learned before that p has to be a factor of the constant. So in this case, it's going to be a factor of the constant negative 6. And we also learned that q has to be a factor of the leading term an. In this case, it's going to be a factor of 1. And so with that, I can go ahead and list all my factors for negative 6. It's going to be plus or minus 1 because you can divide negative 6 by 1. Also plus or minus 2. Also plus or minus 3. And finally plus or minus 6. And at the bottom here, my factor for 1s are going to be just plus or minus 1. And so with that, I can divide these two things, and all I'm going to get here is plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. So some of these numbers could actually be potential 0 for our polynomial. So I'm going to go ahead and test each of them to see which one actually is 0. So I'm going to go ahead and start with 1. So if I plug 1 into my function f and I get a 0, then 1 has to be a 0 for f of x. And so therefore, I'm going to have f of 1 equals to 1 cubed is 1, plus 2, 1 squared is just 2, minus 5 times 1 is just 5, minus 6. All that together will give me negative 8. And so since that's not equal to 0, 1 is not a 0 for this particular polynomial. So I'm going to throw that away. Next, I'm going to go ahead and test 2 to see if that works out. F of 2 here is going to be equal to 2 cubed. It's going to be 8, plus 2 times 2 squared is going to be 8 again. And then minus 5 times 2, that's going to be negative 10, minus 6. And so all these together would give me 0. What that means is that 2 is a 0 for my polynomial. And so since I know that, I can actually be certain that x minus 2 is a factor for my polynomial. So what I'm going to do here is I'm going to go ahead and divide my polynomial by the factor x minus 2 to see what's left. And so for the division here, I'm going to use the synthetic division, which is something that we've learned in note 39. So if you want to know more about that, go ahead and check note 39. And so here I'm going to have 2 on the corner here, and then I'm going to copy my coefficient for the polynomial. It's going to be 1, 2, negative 5, and negative 6. Then I'm going to start the synthetic division. First, I'm going to bring down the 1. Then I'm going to have 1 times 2 equals to 2. Then adding those two numbers here are going to give me 4. Then I'm going to repeat the process. 4 times 2 is 8. Negative 5 plus 8 is 3. 3 times 2 is 6. Negative 6 plus 6 is 0. Of course, the remainder has to be 0 because 2 is a 0 for the polynomial. And so what I'm going to get here is that these three numbers here represent the coefficient for the other factor making up the polynomial. And so I'm going to write my polynomial as f of x equals to x minus 2, coming from the 0, 2, in parentheses, x squared plus 4x plus 3. And so with that, since I have this as a quadratic now, I can go ahead and just factor it out because quadratics are easy to factor. So I'm going to go ahead and write x minus 2 here. Then I'm going to look for two numbers that are adding up to 4 and multiplying to 3. And so those numbers are going to be 3 and 1. And so with that, I have my polynomial written in factored form. So I can go ahead and set each of those different factors equal to 0 in order to solve for my zeros. So I'm going to have x minus 2 equals to 0. That's going to give me x equals 2. Then x plus 3 equals to 0 will give me x equals negative 3. And finally, x plus 1 equals to 0 will give me x equals negative 1. And as you can see here, x equals 2, x equals negative 3, and x equals negative 1 are actually part of our list of guesses that we had up here. And so, that was a good list to begin with. But as far as strategy goes, I will not go ahead and test all of these numbers to figure out which ones are zeros and which ones are not. If I find one and I get myself to a quadratic, I can just stop there and factor the quadratic like I'm used to, and then I'll be done. And so it could turn out that sometimes you would have so many different numbers from the rational zero theorem, and potentially testing all of those numbers would take a very long time. And so there's another rule that we can use here to figure out exactly how many positive real zeros we have and how many negative real zeros we have, potentially. And so that's going to be called the Descartes rule of sign. What that says is that the number of real zeros for the polynomial is going to be equal to the number of sign change in f of x, or that number minus a multiple of 2. And the number of negative real zeros is going to be equal to the number of sign change in f of negative x, or that number minus a multiple of 2. And so what does that mean for this particular problem we just finished? If you look at f of x here, you can see that f of x here only has one sign change. What that means is that f of x only has one positive real 0. And so since in our work here we figured out already that 2 was a 0, we could have just gone ahead and canceled 3 and 6 because we know that we only have one positive real 0. Also, if I write f of negative x here, that's going to be equal to negative x cubed plus 2x squared plus 5x minus 6. And if you look at this guy here, you have one sign change here and another one here. What that means is that the polynomial f of x would have either 2 negative real 0 or 0 negative real 0. Because remember, the number of real 0 is either going to be equal to the number of sign change or the number of sign change minus a multiple of 2. Okay, so let me give you one last example where I'm going to use both the rational zero theorem and Descartes' rule of sign so you can see what I'm talking about here. So we're going to have here f of x equals to x to the power of 4 minus x cubed plus 2x squared minus 4x minus 8 equals to 0. And so here's our polynomial, and we're trying to find the zeros of this polynomial. So again, since this is a polynomial with integer coefficient, I can go ahead and use the rational zero theorem to figure out the list of potential zero for this particular polynomial. So I'm going to have that as p over q, where p is a factor of negative 8 and q is a factor of 1. And so if you have that, the list of numbers that you can have here is going to be plus or minus 1, then we're going to have plus or minus 2, then we're going to have plus or minus 4, and finally plus or minus 8. So all of these are potential zero for our polynomial. And then let's use the Descartes rule to figure out how many positive real 0 we have and how many negative real 0 we have potentially. And so we're going to notice here that f of x has 1, 2, 3 sign change. And so what that means is that this f of x polynomial is either going to have 3 positive real zeros or 1 positive real 0. And if you look at f of negative x, that's going to be equal to x to the power of 4 plus x to the power of 3 plus 2x squared plus 4x minus 8. And if you look at this, you see that this has only one sign change. What that means is that our polynomial only has one negative real 0, and that's it. And so, with that in mind, we can go ahead and start testing our 0 here. So I'm going to go ahead and test 1 to see if that works out. F of 1 here is going to be 1 to the power of 4, which is 1, minus 1 to the power of 3, which is 1, plus 2, 1 to the power of 2, which happens to be 2, minus 4, minus 8, that's going to give me negative 10. And so 1 is not a 0 here. Let me go ahead and test negative 1. So f of negative 1 here is going to be negative 1 to the power of 4 is 1, minus negative 1 to the power of 3, which happens to be also 1 because of the double minus, plus 2 times negative 1 to the power of 2, that's going to be 2, plus minus 4 times negative 1, which is going to be plus 4, and then minus 8. And if you add up all of these things, you're going to see that that's going to give you 0, which means that negative 1 is actually a 0 for our polynomial. So since I know that, I'm going to go ahead and divide the polynomial by x minus minus 1 to figure out what my factors are. And so I'm going to go ahead and use the synthetic division again. I'm going to have negative 1 here in the corner. Then I'm going to have the coefficient of my polynomial. That's going to be 1, negative 1, 2, negative 4, negative 8. And so I'm going to go ahead and bring the 1 down. Then 1 times negative 1 is going to give me negative 1. So negative 1 plus negative 1 is negative 2. Negative 2 times negative 1 is 2. 2 plus 2 is 4. 4 times negative 1 is negative 4. Negative 4 plus negative 4 is negative 8. Negative 8 times negative 1 is 8. Negative 8 plus 8 is 0, of course. So what this means is that the 4 coefficients right here represents my order factor. So I'm going to have here f of x equals to x minus minus 1 in parentheses multiplied by x cubed minus 2x squared plus 4x minus 8. And so with that, since our order factor here is in degree 3, I still cannot go ahead and factor it easily. So I'm going to go ahead and keep checking those numbers to see which ones are potential zeros again. And of course, since you find out that negative 1 is a 0, from the Descartes rule, you know that you only have one negative 0. So that means that -2, -4, and -8 cannot be potential 0 for this particular polynomial. So if you were to continue checking this 0, you would ignore these extra negative zeros. And so that's what the Descartes rule does. It reduces the amount of 0 you have to test. So I'm going to go with f of 2 this time, and f of 2 is going to be 2 to the power of 4 is 16, minus 2 to the power of 3, which is -8, plus 2 times 2 to the power of 2, that's going to be 8, minus 4 times 2, that's going to be -8, and then minus 8. If you add up all of these things, you're going to get 0. And so with that, you can go ahead and do the synthetic division again on the cubic factor of this polynomial. Also, notice that when I tested 2 here, I went ahead and plugged it into my general form of the polynomial at the beginning. You don't have to do that. You can also plug it into this factored form here, but it's whatever you like. So with that, I'm going to go ahead and divide my cubic. So I'm going to have 2 here on the corner. Then I'm going to have the coefficient of my cubic here, 1, -2, 4, and -8. And so with that, I'm going to go ahead and bring the 1, and then I'm going to do 1 times 2, that's going to give me 2. -2 plus 2 is going to give me 0. 0 times 2 will give me 0. Then 4 plus 0 is going to be 4. And then 4 times 2 will give me 8. And then -8 plus 8 will give me 0, of course. And so now I'm going to have f of x equals to x plus 1 in parentheses, multiplied by x minus 2 in parentheses. And then using the 3 coefficients here, I can write the last factor as x squared plus 4. And so with that, I can go ahead and set each of those factors equal to 0. And so I'm going to have x plus 1 equals to 0, giving me x equals -1, of course. Then x minus 2 equals to 0 would give me x equals to 2. And so finally, I can go ahead and set x squared plus 4 equals to 0. And that's going to give me x squared equals to -4, which if you take the square root on both sides, you're going to get x equals to plus or minus 2i. And so with that out of the way, next time we're going to start moving into the direction of drafting rational functions, which are really just polynomial divided by polynomial. And so for my next video, I'm going to talk about how to find the asymptotes of rational function. And as usual, if you would like a PDF copy of this particular note, check out the descriptions below. If you like the way I break down the material, give me a thumbs up, and I'll see you in my next video. Bye-bye.